Hi everyone, I am Zhao, and I am delighted to share our work on improving prosody from Nerd F0 Codebook representations for VQ-VAE-based speech waveform reconstruction. My presentation mainly consists of 6 parts. Firstly, I will generally introduce the background and the VQ-VAE, then I will explain our proposed framework and show the experiment. Finally, I will give the conclusions. Speech signals contain rich factors existing at different linguistic layers, such as prosody, content, and timbre simultaneously. Modeling and controlling these factors through neural representation learning is essential for many speech applications. VQ-VAE is a promising representation learning approach suitable for such tasks as voice coercion and text-to-speech. However, previous works which use VQ-VAE structure for voice coercion tasks have pointed out that superfragmental features, such as F0, are not properly modeled in the voice coercion framework. From a preliminary experiment, we also found that VQ-VAE-based speech waveforms typically have inappropriate prosodic structure in the case of Japanese. In Japanese, pitch directly affects the meaning of the words. For example, hashiga means chopsticks, hashiga means bridge, hashiga means end. Thus, in this paper, we aim at improving the pitch accuracy under VQ-VAE framework. VQ-VAE is a self-supervised learning technique that uses an encoder network, VQ codebooks, and a decoder network. The VQ-VAE is generally trained using a patternized log-likelihood function. The first term is a log-likely function of the decoder network that mirrors appropriateness of reconstructed speech waveforms. The second term derives the quantized vector towards the raw latent vectors. The third term is a penalty term that prevents the output of the encoder from growing arbitrarily large. Our proposed extension is quite straightforward. We extended the VQ-VAE structure by introducing 2 encoders. One of them uses a raw speech waveform as input, as the original VQ-VAE does. The other encoder uses an upsampled F0 trajectory as the input. The loss function can be defined in a similar way by adding a commit loss and a codebook loss for the F0 encoder and vector quantization optimization. Encoders for raw waveform and F0 share the same architecture. Each of them has 10 downsampling blocks. Each block consists of a 1 deconvolution layer and a gated activation layer. Outputs of the gated activation are further filtered using 1 deconvolution. The decoder was implemented using a combination of upsampling blocks, downsampling blocks, and a variant modular. The upsampling block is used to upsample the code vectors to make them at the same operating rate as the waveform points. In the downsampling blocks, the past course components are downsampled and combined with the next code vectors. There are 3 downsampling blocks. The output of each one is connected to the corresponding upsampling block like a Usenet. In our framework, variant is used as a vocoder, and the global condition is inserted as an additional input to all layers in the decoder. We used 3 types of global conditions in our experiment, including the gender encoder, emotion encoder, and the speaker encoder. In our experiment, we combined the JVS compass, JTES compass, and an in-house compass introduced in our previous work in order to augment training data. There are 212 speakers in total. We selected 8 speakers and 10 entrances per speaker as the test set. Our test speakers are completely unseen and omitted from both training and validation set. Results for each test speaker and the average are shown in Table 1. We can see that the proposed extension reduced the F0 distortion for all test speakers as expected. Moreover, we can see that reconstructed speech using the extended VQ-VAE generally has higher mode score than that using the original VQ-VAE. We conducted an A/B preference test and compared the VQ-VAE with and without the F0 encoder subjectively. As we can see from the table, our proposed extension has achieved significantly higher preference scores than the original VQ-VAE for all the test speakers, and this clearly demonstrates that the extended VQ-VAE NERD complementary superfragmental features which are critical for human perception. Now, let's listen to some samples. The first sample is a male speaker. Firstly, it's his nature speech.
また、当時のように五大明王と呼ばれる主要な明王の中央に配されることも多い。
Next is his reconstructed speech using the original VQ-VAE structure.
また、当時のように五大明王と呼ばれる主要な明王の中央に配されることも多い。
The next is the reconstructed speech using the proposed extended VQ-VAE structure.
また、当時のように五大明王と呼ばれる主要な明王の中央に配されることも多い。
The next is a female speaker. Firstly is her nature speech.
サービスマネージャー導入駅のため、大井町駅から遠隔管理している。
Then is his reconstructed speech using the original VQ-VAE.
サービスマネージャー導入駅のため、大井町駅から遠隔管理している。
Next is her extended VQ-VAE reconstructed speech.
サービスマネージャー導入駅のため、大井町駅から遠隔管理している。
If you wish to listen to more samples, please visit our website. We also trained a speaker-dependent VQ-VAE without and with the F0 encoder using the Mandarin database to analyze what happens in another language. From the table, we can see that the proposed extension effectively reduces the F0 distortion for the Mandarin speaker. The RMSE value for the Mandarin speaker is smaller than those of the Japanese speakers, but this is not surprising since the Mandarin model is speaker-dependent, whereas the Japanese model is speaker-independent. This paper proposed an extension of VQ-VAE for learning F0-related superfragmental information. Additionally, the extended framework uses a F0 trajectory as additional input and learns discrete representations for F0. Experiment on Japanese databases shows that reconstructed speech of extended framework has lower F0 RMSE for all unseen speakers, and the listening test also indicated significantly higher preference scores. An additional experiment using the single-speaker Mandarin database also shows the proposed model reduce F0 distortion in another language. Our future work will include the evaluation of the downstream tasks using learned discrete representations, such as TTS and explicit disentanglement of latents for F0 and waveforms. This is the end of the presentation. Thank you very much for your listening.